Hello everyone, in this video we're going to be looking at section 11.3, which is the dot product of two vectors. Okay, so let's just start with the definition of a dot product. The dot product of two two-dimensional vectors, u and v, is, we denote it by u dot v, so that's why it's called the dot product. And it's just the first component of the first one times the first component of the second one plus the second component of the first one times the second component of the second one. And then the dot product for the three-dimensional, two three-dimensional vectors is just the exact same thing, except we also add the third components being multiplied together. So one thing we should notice right off the bat here is the dot product of two vectors is a scalar, right? In other words, it's a number. It's not another vector, right? So the dot product of two vectors is a scalar. Now some properties of the dot product. If we have u, v, and w that are vectors and c is a scalar, it's commutative. It's got a distributive property. 3 is kind of interesting because it basically says that I can take the scalar either to the first component or the second component. I'm sorry, the first vector or the second vector that's being multiplied by when you multiply a dot product times a scalar c, you can either multiply it times the first vector or the second vector. That's what I was trying to say. V dot 0 or 0 dot v is always going to be 0. And if I take a vector and dot product with itself, it's equal to the magnitude of that vector squared. All right, so those are just some interesting properties about the dot product. Now let's practice computing the dot product. Okay, so let u equal to that vector, v equal that vector, and w equal to that vector. Now let's find u dot v. So u dot v again is going to be 2, -2 dot 5, 8. And what I can do here again is just first component plus second component. So this one's going to be 2 times 5 plus -2 times 8. So we get 10 minus 16, which is -6. And that's what we expected, right? Because the dot product is a scalar, right? It's a number. Okay, so for this next one, I have u dot v times w. So what do we expect to get? In this case, I take u dot v, which is a scalar, and then a scalar times a vector is going to give me a vector, right? So I expect my answer to be a vector. Hope if I can spell it right. There we go. So what do we find u dot v to be equal? So we'll just say u dot v times w. U dot v, that's what we found in the previous answer. So this is -6. And then what is w? That's -4 times 3. And then we know if we have a scalar, we distribute on the inside. So here I get positive 24 and -18. So I get a vector here. Okay. And then now if I do u dot 2v, let's think about what we expect to get here. U dot 2v, 2v itself is a vector. U dot vector is going to be, this is going to give us a scalar, right? Because it's essentially just the dot product of two different vectors. But if we look at property 3 here, what does property 3 say? It says if I take one of my vectors and it has a scalar multiplied to it, then I can rewrite that scalar on the outside. So in other words, I can kind of use like this side here and go out this way. So if I want to rewrite this, u dot 2v, I could rewrite this as 2 times u dot v by property 3, right? And now what we say u dot v was, u dot v, that's what we found in part A, which is -6. So I have 2 times -6, which is going to give me 12, which again is a scalar like we expected it. All right, and then finally the magnitude of w squared. Well, by property 5 here, the magnitude of w squared is going to be w dot w. All right, so this is equal to w dot w. So this would be -4 times -4, in other words, -4 squared plus 3 squared. right? Because negative 4 times 4, and then 3 times 3. So I end up getting 16 plus 9, which gives me 25. Okay, so now let's talk about the angle between two vectors. This is an application, this will end up being an application of the dot product when we look at theorem 11.5 here. Okay, so the angle between two non-zero vectors is the angle theta, where theta is between 0 and pi, between their respective standard position vectors. So in other words, if I have this vector here, say this is vector u, and I have this other vector here, say this is vector v, then theta is going to be just this angle between these two, right? And remember, what is this vector here? I can go ahead and just label this in the picture for fun. This vector, I'm struggling with that arrow. There we go. This vector is u minus v, right? Or I'm sorry, in this case it would be, yeah, I'm right. Okay, so that is what the angle is. Again, it's just the angle between, if you put their tails together, right? Okay, so if theta is the angle between, and this is, I'm sorry, I should probably say this is the origin, right? Okay, if theta is the angle between two non-zero vectors, u and v, where theta is between 0 and pi, again, in this situation where, in the picture that I drew above, then cosine of theta is equal to the dot product over the magnitude of u times the magnitude of v, right? So that is our formula there that's going to allow us to solve for theta to find the angle between two vectors. So because the magnitude of u and magnitude of v, remember what's that formula? It's like the square root of everybody squared. So those guys are all positive. This guy and this guy are positive. So if these two are positive, what does that mean? That means that u dot v and cosine of theta will always have the same sign, right? So if u dot v is negative, then cosine of theta is negative, and if u dot v is positive, then cosine of theta is positive. So that's just something to note. Okay, definition of orthogonal vectors. So two vectors are orthogonal when u dot v is equal to 0. Right, so that is our way of knowing if they're orthogonal. Remember, we found in the last video that two vectors are parallel if u is equal to some constant times v, right? That was parallel. So now, how do we know if they're orthogonal? That means that u dot v is equal to 0. So this implies that two non-zero vectors are orthogonal if and only if the angle between them is pi over 2. Right, and that just comes from this formula up here. If u dot v is equal to 0, then when is cosine equal to 0? At pi over 2. Right, and that makes sense because we think about, I always just think about that being pi over 2 and 0 make that a right angle, so that's kind of an easy way to remember it. Okay, so one thing to note here is just some terminology, but the terms perpendicular, orthogonal, and normal all essentially mean the same thing. Right? And they just mean you make a right angle. So why are there 3 different terms for that, and when do we use those different terms? Well, typically, again, this is more convention than it is anything stated specifically in the texts, but two vectors are orthogonal. So anytime we're talking about vectors, we say that they are orthogonal. We don't say parallel. We don't say perpendicular or normal. Two lines or planes are perpendicular. Right, and that was probably the first word you learned out of these 3 words, orthogonal, normal, and perpendicular. You probably learned perpendicular first because that's what you learn in grade school when you start talking about lines being perpendicular. And then a vector is normal to a plane or a line. So that's the case when we start talking about normal. Okay, so for the pair U, V, and W, I'm sorry, for U, V, W, and Z, find the angle between each pair of vectors. Right, so essentially we're just going to be using our formula right here. So in order to use that formula, we need to know U, in this case, since we're doing it between U and V, we need U dot V and the magnitude of U and the magnitude of V. Right, so U dot V is going to be 3, -1, 2, dot -4, 0, 2. And that's going to give us 3 times -4. So that's going to give us -12 plus 0 plus 4, which is going to give me -8. So now I need the magnitude of U. The magnitude of U is going to give me, again, that's every component squared underneath the square root. So here I get 3 squared plus -1 squared plus 2 squared, all underneath the square root. And that's going to give me, I get 9 plus 1 plus 4 is going to give me 14. So I get square root of 14. And then the magnitude of V, here I will get -4 squared plus 0 squared plus 2 squared. So that's going to give me 16 plus 4, so radical 20. So now what do we know by our formula? Well, we know cosine of theta is equal to U dot V, which is -8 over top of radical 14 times radical 20. Right? And that means that cosine of theta is equal to -4 over radical 70 if I simplified that. So that means that cosine inverse, well actually so let's just say theta is equal to, right, if I take cosine inverse of both sides, theta is equal to cosine inverse of 4 over radical 70. And if I plug that in my calculator, I get 2.069 radians. Right, so that is my angle. And if I notice that the dot product of U and V is -8, so cosine of this angle would also be negative, right? Okay, so let's look at U and W. So I'm just going to go ahead and do this so that way I don't have to keep rewriting it. Okay, so U and W, so again I need U dot W, which is going to be 3, -1, 2, dot W, which is 1, -1, -2. So what is that going to give me? That's going to give me 3 plus 1 minus 4, right, when I multiply all those components together. So that's going to give me 0. Hey, something cool happens when the dot product's equal to 0, right? Since the dot product's equal to 0, we know that U and W are orthogonal. So because they're orthogonal, we're expecting the theta between them to be equal to 0. So let's kind of show why that is. So the magnitude of U is going to be 3 squared plus -1 squared plus 2 squared, which is going to give us, I think we already did this one, 14. The magnitude of W is going to be 1 squared plus -1 squared plus -2 squared underneath the square root, which is going to give us 6, radical 6. So cosine of theta is equal to U dot W, which is 0 over radical 14 times radical 6. Well, that's just 0. Right? 0 divided by a constant is 0. So I get that theta is equal to cosine inverse of 0. Well, when is cosine 0? Cosine is 0 at pi over 2. Right? So just as we expected, the angle between them was pi over 2. because they were orthogonal. All right, but we just kind of showed our work there. All right, so now let's look at v and z. So v dot z. So v is going to be negative 4, 0, 2. Z is going to be 2, 0, 1. So here I get negative 8 plus 0 plus 2, which is going to give me negative 6. Not negative 6. Sorry, z should be negative 1 here. Right, 2, 0, negative 1. So this should be a minus 2, which gives me a minus 8. That looks better. Magnitude of v, I'm pretty sure we already solved for here up top. That was radical 20. And then the magnitude of z, that one's going to be 2 squared plus 0 squared plus negative 1 squared. So that's just going to be radical 5. So I get that cosine of theta is equal to negative 8, right? That's u dot, or v dot z over top of radical 20 times radical 5, which is going to give me, sorry, I screwed that up again, didn't I? Negative 2, 8 minus 2, this is negative 10. Here we go. Negative 10, so I end up getting negative 10, and then here 20 times 5 is going to give me 100, so I get square root of 100, right, which is, it's just going to be negative 10 over 10, which is negative 1. So I get that cosine, or theta is equal to cosine inverse of 1, and that means that theta is equal to pi, right? Remember, theta is equal to pi is actually going to mean that they are parallel. Right? If the angle between them is pi, that just means they're kind of pointing in the same direction, so they are in fact parallel. So here v and z are parallel. In fact, v is equal to negative 2z upon further inspection, if you look at that here. Right, if I multiply v times, or z times negative 2, I will get that. All right, let's go ahead and end this video here, and we'll pick up in the next video with projections.